So now we're going to step into approximate integration. Now, I just wrote this yesterday, or rewrote it yesterday. So I might jump around a little bit in the lecture to kind of make sure that we get to really understand it. And I guess since we have 20 minutes, it's going to be good to get an overview of what I mean by approximate integration. So approximate integration is what should be called numerical integration. So I would prefer this to be called numerical integration because that's really what we would call it in use. It's numerical integration. Numerical integration basically means that you're handed an integral that has no antiderivative, where the integrand has no antiderivative. So I write that in a paragraph here. There are two types of functions we cannot integrate. Those without a closed form antiderivative. For example, this right here. Good luck integrating that. Have fun. You will not be able to integrate it no matter how you try. That is a non-elementary function, which means it is not integrable. You cannot integrate e to the x squared. So that's one of the infinite number of types of functions you cannot integrate. And then there's another set of, I don't want to call them functions, but there's another style of problem that when asked to integrate, you'd be stuck. And that is problems consisting of only finite data points. In other words, real world problems. Because in the real world, people are going out and taking measurements. They're polling for opinions, that type of thing. And there's no function for the data points they get. They get a bunch of data points. It's a bunch of scattered data points, but they don't have a function that fits that data set. So instead, they just say, well, I have these 3 billion points or whatever it is. And integration is so powerful, it can be used for a lot of things. Specifically, it can be used to sum data very quickly. But with discrete data, like finite data points, to use integration to sum that data up, you would like faster methods than what we already know. Now, just to let you know, we happen to already know how to integrate numerically. We have the left endpoint method, and we have the right endpoint method, and we have the midpoint method. Those are the three introductory methods. Now, I say introductory methods because the reality is that we have, I'm going to throw a number out there that's probably too small, but we have around 30 methods or more. That's why I said I threw a number out that's somewhat small. My focus, part of my focus in upper division mathematics was investigating numerical integration techniques, or numerical techniques. Numerics is what we'd call it. And so in that course, it was a 3-quarter course, and all you did was just new methods all the time. So there are a ton of different methods to do these. In this section, we're just going to introduce 2 new ones. Okay. So numerical integration, the definition: using sample points, which is discrete points, instead of a continuous interval to approximate the integral value is called numerical integration. And again, many methods are created to numerically integrate. However, we focus on 5: the left endpoint method, the right endpoint method, the midpoint method, trapezoidal rule, and then Simpson's rule. Now, I want to showcase what these are. And yes, my last name is Simpson, but no, that's not my rule. So I think it's best to get that out of the way because people think that that's dedicated to me. No, it's not. Let me go ahead and showcase these methods because it's good to see what they are. So let me hop over here. So here's a function. Let me make sure that it's popped up on my end too. There we go. Yeah, okay, good. I just want to make sure I could see it on my laptop. All right, so here's a function, e to the negative 2x. In fact, I guess that's okay. And if you take a look at this, if you do left endpoints, you get something like that. This is 4 slices, by the way. We've done this. The approximate area using the left endpoint method here is a 0.77650. Obviously, 4 slices, that's not going to be great. The exact area is 0.49084. So you can see the error there. Pay attention to this error. I just want you to be very aware of the error. It's 2.86 times 10 to the negative first. In other words, we're off by 0.286 from the exact value. Now let's look at the right endpoint method. The right endpoint method, at least in this case, is slightly better. The error is a little bit less, but it's still pretty far off from the exact value. Now let's look at the midpoint method, which is a method that we've seen before. And this time I'm going to scroll up so you cannot see the error. That's the midpoint method. Notice we still have 4 slices, but in each interval, we're using the height at the midpoint of that interval. So the mid x value of the interval gives us the height of our rectangle. And here goes the trapezoid method, the newer one that we're going to delve into. The trapezoid method, just to give you an idea before I click on it, is it's going to still have 4 slices here. However, we're going to connect the height on the right edge of this slice to the height on the left edge of this slice. So watch what happens. Now, you're going to look at that and say, holy moly, that's got to be good. That's got to be a really good approximation. And if I scroll down, you'll see, look at that error. That's actually pretty small. Remember, my errors before were around 2 times 10 to the negative first. This is 4 times 10 to the negative second. In other words, 0.04 is the error versus a 0.2. And you say, yeah, that totally makes sense, that this looks like it's going to be a really good approximation. But if I go to the midpoint method, notice the error there is not 4 times 10 to the negative second, but only 2 times 10 to the negative second. The midpoint method is twice as good as a trapezoid method. Pretty interesting how that works. Even though visually the midpoint method looks worse, it actually averages out the errors and ends up being twice as good as a trapezoidal method. So we learned the trapezoidal method only because it's a method it's worthwhile to learn. It's actually faster to compute. And when you do numerical integration or any type of numerical technique, you're really balancing precision with speed. You would like a fast method that's precise, but the faster the faster the numerical method, the less precise it gets. So you want this balance of speed versus precision. Life is full of give and takes. There's not a perfect. And so this is a great example of that. I love this part of mathematics because it just showcases that there's always a balance. If you want a super fast method, if you have 1 billion data points and you want to integrate over those 1 billion data points quickly, you could do that very quickly, but the value is really going to be off from the exact value. But then we get to an incredibly unique method. The incredibly unique method is Simpson's method. And what we do is we take these 4 slices, the same 4 slices, but instead of, like, notice with the midpoint method, we had 4 slices, but we were using yet another group of data points within those slices. So technically we had 8 data points here, technically 9 because of the edge, but whatever. We used more than the 4 data points. We were using the edges. Each slice has 2 edges, but then we also use the center point. And so you need a lot more points to use the midpoint method. Simpson's rule, on the other hand, it takes that same 4 slices and it breaks it into 2 chunks. So these first 2 slices, it's going to connect with parabolas. So notice it's actually n equals 4 here. You can see it right up here. I have 4 slices, but we've broken that in half because we need 2 slices to create a parabola. Simpson's rule creates parabolas, and you connect a bunch of parabolas together. And that is, look how nice the error is. Very small error. Simpson's rule is a super awesome method. You essentially have 4 slices, but you get a lot better approximation for the area underneath the curve. And if I go for, let me see if I can find, let's go for a sine curve. Let's go for, trying to find something that's a little more jagged. Well, this will be fine. Let's say that we have, let's say we did 20 slices, the left endpoint, 20 slices. Look, that's a very small error there. 20 slices, and that's 8.08 is the error with 20 slices. Now let me reduce that down to 4 slices. And let's do Simpsons. And I have less error with fewer slices using Simpsons. So this is where that speed and precision really start to match up nicely. So Simpson's rule is a superb rule to use. Let me go back because I can't see my chat window when I'm on this, so I'm going to go back now. All right. So that's a preview of where we're going. All of our numerical integration techniques, at least at this level, still have these same 2 conditions. Delta x, which is the width of each slice, is always b minus a over n, and x sub I is always a plus I delta x. Those 2 are constant for us for all of our integration techniques at this level. If you want to pursue mathematics or computer science, then the integration techniques you use there will have a delta x that varies depending upon how jagged your function is. And as a reminder, the left endpoint method is the top one there. The right endpoint method is this guy right here. And the midpoint method uses the average x value and plugs that into your function. So those are kind of reminders of our previous methods. And by the way, that this link down here goes right to the animation I was just showing. So forwarding a page. I'll zoom out. This is the trapezoidal rule. This is how you compute. Trapezoidal rule is essentially, not just essentially, it's averaging the y values for your slice. Let me show you this visually because I think it's much better. Where's my ruler? There it is. So you have some function. I'll move this off the screen for the time being. And our function I'm going to draw in blue, the standard function f. And we're just going to look at the ith slice. I'm going to make it an exaggerated ith slice so that we can have a conversation. Okay. This is x sub I minus 1. This is x sub I. So obviously the y value here is f of x sub I. And the y value here is f of x sub I minus 1. Okay. And we want to connect those 2 dots up with a nice, beautiful line to create a trapezoid. That's why it's called the trapezoidal rule. It's because you're creating trapezoids here. So let me just go ahead and connect these 2 dots. It's a great way to describe calculus. What do you do in calculus? I connect the dots. That's all I ever do. So we have connected the dots. We've created a beautiful trapezoid. Now, I don't know if you know about the area of a trapezoid, but the area of a trapezoid is, how do I want to say this? It's 1/2. This is how you learned it in a pre-algebra class. It's 1/2 times height 1 plus height 2 times the thickness of that, the width, I'll say, times width. But we know height 1, let's just call that, is f of x sub I minus 1. Height 2 is f of x sub I. And the width is delta x. That is a good way to think about this. It's the average y value times the width. That's all that is. It's y average. Let me write that down. Y average times the width. That's really what the area of a trapezoid is. It's the average y value times width. Versus midpoint method, by the way, just to remind you, The midpoint method is the average x value. This is an average x value that you plug into your function and then times the width. That's the midpoint method. The trapezoid method looks at the average y value. Okay. So anyhow, take the average y value, yay. And that's what the area of the ith slice looks like. But I'm telling you up here, notice there's a big old formula. This is a closed form formula. This tells us the pattern for the summation. And I'm telling you, even if the curve goes below the x-axis, it still works out. So I did not actually have to place my x-axis below. I could have placed it above. The area would still be the same. It'd be negative, but the computation would still be the same. So it's totally fine. Yeah, it's a good question. So here is the closed formula for the trapezoidal method, and it's super easy and fast to derive. So T sub n, which is the trapezoid method with n slices, is going to equal the area of the first slice plus the area of the second slice plus so on and so forth down the line, all the way to the area of the nth slice. And I think everybody's pretty okay with that. I hope you guys are all fine with that. The area of the first slice is 1/2 times f of x naught plus f of x1 times delta x, plus then the area of the second slice is 1/2 the average y value, which is f of x1 plus f of x2 times a delta x, and so on and so forth down the line. The area of the n minus first slice is 1/2 f of x sub n minus 2 plus f of x sub n minus 1 delta x. And the area of the nth slice is 1/2 f of x sub n minus 1 plus f of x sub n delta x. Now, I hope you realize all of those have a half in common and a delta x in common, so I'm going to factor those out. And you'll be left with f of x naught plus f of x1 plus f of x1 plus f of x2 plus dot, dot, dot. There'd be another f of x2 over here, by the way. Keep going. Plus f of x sub n minus 1, 2, sorry, plus f of x sub n minus 1, plus, that's this guy right here, plus another f of x sub n minus 1, and then finally plus f of x sub n. Now, you should have 2 of all of those f of x sub whatevers. Every single one of them, you should have 2 of them, except for the left and right edge. Because, well, the left and right edge of this entire interval only occur once. X sub 0 is right here. X sub 1 gets used to compute this area, but also gets used to compute the next area. So, but x naught and xn only get used once. And so you can see that in the summation that this will be delta x over 2 times 1 of those f of x sub zeros plus 2 of those f of, geez, my ink is just doing terrible today. 2 of those f of x sub 1s plus 2 of those f of x sub 2s, so on and so forth down the line until you get to 2 of those f of x sub n minus 1s plus a single f of x sub n. And that is the proof. We've actually just reached this. That is the area underneath the curve using a trapezoid rule. Very, very nice. So we are done for now. On Monday, we'll actually go into computing them. They're very fast. This whole section is super fast. So I still do extra examples via video, so you have some other resources, But to be honest with you, numerical integration, most people really like because you just plug and shell. You just plug things in. There's no calculus involved. It's just remembering this formula and one other formula, which we'll derive on Monday. All right. It is 8:50. So you guys are free to go. I'll be here until 9:50. I'm going to take a 10-minute break. But if you're not in office hours, then I hope you have a wonderful weekend. If you are in office hours, I hope you have a wonderful weekend as well. So have a wonderful weekend, everybody. And I'll see you on Monday. I'll be back in 10 minutes. All right. Take care.